I guess it's not. Okay. So we have the gravity here. And so then we'll bring it over here and we'll plug it into this equation. And so we'll say mass times gravity is equal to G m1 m2 over r squared. Um, and so one of our masses is going to cancel out. The gravity that we found here is this 3.3 meters per second squared is equal to G, and then m2, we're going to take this one over r squared. And from there, we'll solve r squared is equal to um, G over 3.3 meters per second squared. And that you just plug into your calculator, and it should give you this. Okay. Do y'all have any questions over this? Or I'm just gonna keep moving, and then if anyone has any questions, just either put it in the chat or like unmute. Um, but yeah. Okay, so we have this 1,000 kg car. He's on a flat circular road with a radius of 100 meters. So we're given force of friction between the car's tires and the road is 5,000 newtons. And so how fast can the car drive without slipping on the track? Um, so if you remember, force of friction only works up and down. Um, but we're gonna take this, right? So our centripetal acceleration, that's gonna be the thing that like allows the car to keep turning, right? Um, and so we're gonna set this equal to the force of friction provided. So we're gonna say this. And then from there, you'll just calculate. So you'll say 1,000 kg v squared over 100 meters equals 5,000 newtons. And so you get uh, this, and then you take the square root of 500 newtons, which gives you 22.36 meters per second. Um, so yeah, that's number two. And so this one is number three. We're given this pendulum. We're told it's 0.50 kg. And so we're given a length is equal to 1.0 meters. Now, as it swings through the bottom, it has a speed of 1.5 meters per second. So when the pendulum is at this point, what is the tension in the string? Um, so again, if you'll remember, we have our free body diagram. So at the bottom, we're going to be dealing with mass times gravity. And then the tension will be supplying the, it'll be counteracting the mass times gravity, and it'll also be supplying the centripetal acceleration. Um, so from there, we get tension is equal to AC plus mass times gravity. Um, and then we can solve from here, and we say this, mv squared over r plus mass times gravity, and 0.50 kg times meters per second squared over R is equal to 1 meter plus mass 0.50 kg times gravity, which obviously is just G, right? So then you calculate and you get 6.025 newtons. And then that's your answer. Okay, so that's 1 through 3. This is another satellite question. So we're given circular orbit of radius 1.50 times 10 to the 7th, and we're also given this mass. And so we're asked, how long does it take for the satellite to complete one orbit around the planet? And so this formula that we use, because we're tasked with time, finding this time, we're going to use this formula, T equals 2 pi r over velocity. Okay, and then from here, we'll take, um, let's see. From here, we don't have velocity, so that's probably something that we'll have to solve for, right? So, let's see. Actually, I think there's a faster way to do this. I think you can use, instead of using that formula, you can use this formula right here. Um, so we can say then T equals 2 pi r 3/2 over square root G mass of Earth. And so we say then this T is equal to 2 pi. Radius is 1.50 times 10 to the 7th, quantity to the 3/2. So times 10 to the 7th. And then RG, and then mass. We're gonna, instead of using mass Earth here, we'll use this mass given. So we'll have this. Okay. And then you just solve and you say this. And this gives you, which is close enough to this. So note that the G used here, oh, what's this question? Do I think the exam will be harder or easier compared to our last exam? Um, I think that's sort of up to you. Um, I definitely think that the formulas and like the math for this exam is easier than the first one. Um, but I think conceptually it's a little bit harder. Um, and it's gonna be basically the same as the old exam. So as long as you know this, I think you'll be okay. So yeah. Okay, let's do 5. Say the astronaut weighs on a scale on Earth to be 735 newtons. So let's say this on Earth, he is 735 newtons. And then on another planet, So let's call this planet X or whatever. It's 1400 newtons. So if the planet has a radius of 5 times 10 to the 6 meters, what is the mass of the planet? So again, we'll probably be using this formula, right? Okay. And so the difference between Earth and planet X um, is not going to be the mass of the person, but it's actually going to be the gravity that's different. Um, so we can say that the difference between, or like how to get between 735 newtons and 1400 newtons, we can just divide, and then that's the amount the gravity is bigger. Um, so when you divide, it gives you like this is basically the mass of Earth times 1.9. So the gravity times 1.9 here. Oh, this is gravity here. Um, so that's that one. And then you'll plug it into here again, and we'll say this mass times gravity times 1.9 is equal to G m1 m2 over r squared. So one of these cancels out, and we're left with um, basically just solving for the remaining mass. So we can say this now. Okay. And then when you plug this into your calculator, you should get this. Okay, so that's 5. Um, Moving on to 6, we're given the bicyclist wants to perform a stunt of riding on a track that goes in a vertical loop. If the loop has a radius of 3.5 meters, what is the minimum speed the bicyclist needs to have at the top of the loop in order to not fall from the track? So let's just draw a picture first. So he goes through this loop here. The loop has radius r is equal to 3.5 meters. And so at the top, this is the same as like the bucket one. I think actually we covered this in recitation. Um, but we have basically at the top, we have mass times gravity, and what's keeping it in the circle is centripetal acceleration, and this will be provided only by gravitational force. So from here we can say this, and now we cancel again, rg root equals velocity. Now we solve for velocity, and we should get the answer from there. Yeah, okay. All right, and then 7. So we're told that there's this child on a merry-go-round with radius r is equal to 1.5 meters. The child has speed 3 meters per second. What is the smallest coefficient of static friction that will keep the child from slipping on the merry-go-round? Okay, so if we're going to be working with static friction, the smallest coefficient, we know we're going to be solving for this mu k. So mu k. And so now we have force of friction equals mu k times n is probably how we'll get there, right? Um, and so this force of friction is going to equal actually the centripetal force. Um, so now we can say this is equal to force of friction. So mass v squared over r is equal to mu k mass times gravity. And from here we can actually cancel out the masses, right? And we just solve and we say right? Because we plugged in for velocity squared, we said 3.0 meters per second squared over our radius, 1.5 meters times our gravity, and then that gives us our answer. So that's number 7. Um, okay, I think we did this one in recitation. We did this one. Um, we did this one. We did this one. Okay, I don't think we did 17. So we're told that the blocks are held by like this light spring in the middle. Um, and so block A has mass 4 kg, block B has mass 8 kg. The two blocks are released from rest and slide off in opposite directions. And then block A is going to move to the left with a speed of 6 meters per second. The spring was non-attached, and so it drops to the floor. So we're solving for this final, or we're solving for this initial elastic potential energy. Oh, yeah, actually mu static is right. I just memorized it as mu kinetic. Um, like mu k is just like what you would call it for if it was moving. Um, but yeah, technically it should be mu static, but it's the same thing, at least like when you solve it mathematically. So yeah, okay. So this one we're gonna use momentum into energy to solve. So this is momentum and energy. So as this block moves to this side, um, the momentum here, again, let's set up like our plus and our minus over here. This is 24 kg meters per second. And then this is going to allow us to solve for the 8 kg. So we're not told what this velocity is over here, right? But based on conservation of momentum, this initial momentum initial is equal to 0. And so our momentum final has to also equal 0, right? So momentum initial equals momentum final. 0 equals momentum final. And so then we can say 0 is equal to negative 24 kg meters per second plus whatever this is, this question mark. So we'll say um, mass B 8 kg times velocity of block B. And this gives us 24 kg meters per second is equal to 8 kg velocity B, giving us velocity B moving to the right at 3 meters per second. Okay, and so what we can do from here is we can calculate energy. And so we can say um, our kinetic energy is equal to the elastic potential energy. Okay, and so then we say, let's move this. Now we say 1/2 mva squared plus 1/2 mb squared is equal to elastic energy. And so solving, we say this. And that should give us our answer. Yep. And so energy is equal to 108 joules. So that's 17. Okay, and then 18, we're given two cars. They're moving in like perpendicular to each other. This question is going to be a momentum question. So this is momentum. And basically the design is just to set up like a triangle and say that like momentum here is like momentum is going to give us this, right? So that's basically the design of like what we want to do. So we'll say that momentum A is equal to, let's call this momentum A, let's call this momentum B, let's call this momentum C. So we'll say this 12 kg meters per second. And then our momentum B is going to be this 32. Okay. And then we'll plug that in to here. And what we'll get is, and with this, we can solve by dividing it by this 2000 that's over here. And so to solve for velocity, we say okay, and that's 18. Why is kinetic energy equal to elastic potential? Um, that's because of conservation of energy. So, right, just like the potential energy or like the initial energy is coming from the spring. And so the energy that the blocks get and are able to use once like the spring has no potential energy, um, that's what they're going to be using for the kinetic energy. Um, yeah. Sorry, that's kind of a rough explanation, but yeah. So 18, and then let's do 19. So we're given this 16 meters per second, 4 kg, and the B block is 12 kg. And so we're tasked with finding the final kinetic energy. Um, And so again, this is just going to be another momentum and energy question, right? Momentum. And so we'll say momentum initial equals momentum final. And our momentum initial is 16 meters per second times 4 kg. And then we would include the block B, right? But it goes to 0, so we're just going to say 0. And then our A and our B combined is 16 kg. And let's find our velocity final. And what this velocity final is going to allow us to do is it's going to allow us to plug it into our kinetic energy formula. So that's what we're hoping to do. Um, so we multiply these two together and we get 64 kg meters per second equals 16 kg. Velocity final, leaving us with velocity final of 4 meters per second. Okay, and then from here, we're going to plug it in. So 1/2. And then because it's both blocks A and B, we're going to say 16 kg. And then velocity squared of 4 meters per second squared is equal to kinetic energy. And when you solve, get 128 joules. So that's 19. All right. And then 20. These I feel like are I feel like these are pretty common. There's like always one of these on every exam. But they're relatively simple to do. So we're tasked with finding the coefficient of kinetic friction, or we're tasked with finding distance, sorry. What is the distance d? Um, and so for this, we're probably thinking like energy and momentum. And to solve for distance, we're going to use work energy theorem, right? So let's say momentum and energy. And if you remember, we say work is equal to force times distance, and work is also equal to delta kinetic energy by our work energy theorem. Okay. So let's start with our initial momentum. So we'll say this momentum initial is equal to, do we have impulse on the exam? Uh, yes, there is one impulse question, and I'm gonna go over it in a little bit. Yeah, there's a power question on 23, um, or maybe it's 22, I can't remember. Yeah, it's on 23, but I'll cover that in a little bit. Um, so yeah. Okay. So for our momentum initial and our momentum final, um, momentum initial is mainly going to be supplied from this, right? Because our velocity here is 0. Um, so, and then our momentum final is just going to be the two blocks or the block and the bullet combined, right? So our momentum initial is going to be 400 meters per second times 0.02 kg plus 0, right? And our momentum final is what we're solving for. So we say this. So we have 8 kg meters per second. And on this side, we have 2 kg, right? Because it's this bullet here and this. So together it gives us this 2 kg. So then we also have velocity final. And so our velocity final is 4 meters per second. Okay. And so from here, we can calculate energy, and that will allow us to solve. Uh, so our energy is this 1/2 mv squared. And so solving, we say 0.5 times 2 kg times 4 meters per second squared, or sorry, and we get 16, right? Or this should be in joules. Okay. And since work is equal to delta KE, our final kinetic energy is 0, right? Because this velocity is 0. So that means that the work done is 16 joules, right? So since we know work is equal to force times distance, and the force here that's doing the work is going to be this friction right here, right? And so force of friction is equal to mu k times n, where n is equal to mass times gravity. So we say 0.40 times 2 kg times 9.8 meters per second squared. And we get this. Okay, and so now we're given this 16 joules over 7.84 newtons equals distance. And that gives us our answer. Okay. So I think that rounds out everything that we didn't do on the 2024 exam in recitation. So yeah, I'm gonna do the 2023 next. Um, so let's move this here. Do you guys have any questions or anything else over 2024, or should I keep going? Yeah. All right, so let's do 2023. So we're told a person with weight W sits on a circular Ferris wheel going around at a constant speed, at which point along the path is the normal force acting on the person the greatest in magnitude or it's the same at all points. Um, so just like looking at this, we can eliminate 4 and 2. Like those just aren't going to be right. And so the difference between 1 and 3 is normal force always acts perpendicular, right? So here normal force points up, it's acting perpendicular. So let's just say at point 1. Let me check this and make sure. Yeah, so normal force points up, and we're given this, and then in contrast at point 2, we're told normal force and mass times gravity. and centripetal acceleration. Okay. Um, and so this one's a little bit counterintuitive because like at first you might think that the greatest normal force is going to be here, right? Um, but if you remember that centripetal acceleration is not a force, it's actually, it has to be supplied by something else. When you look at point one, actually what's going to happen is mass times gravity is going to apply a lot of what it normally would exert against the normal force to centripetal acceleration, right? And so that's going to lessen your normal force. But in contrast, since your normal force in at point two, or I guess this is point three, sorry. At point three, since your normal force is pointing in the same direction as mass times gravity, um, it's going to actually contribute some to what's going on here. And so instead of being lessened by what's happening here, it's actually going to be increased. And so like in a real world perspective, when you think about this, if you go down like a roller coaster, and say like your roller coaster is like this, um, like when you start here and then when you start here and then you go down here, you feel like you're heavier at the bottom of this, uh, I don't know, at the bottom of this hill, I guess you can say. But as you go up and like reach this point, like you don't experience that. Oh, shoot, sorry. Wait, that is wrong. The centripetal acceleration does point upwards. Um, yeah, it does point upwards. Yeah, you're right about that. So it points upwards. Um, yeah, yeah. So I guess either way. But I just feel like this is easier to think about, like from a roller coaster perspective. Um, that like as you pass through this bottom, like you feel heavier, and as you pass through this top, it's not. But yeah, thanks for catching that. Sorry about that. Um, yeah, this one I always feel is like really tricky and like really counterintuitive. It doesn't make any sense. Um, but yeah, so okay, let's move on to two. Um, so we have this 0.1 kg stone connected to a string in a uniform horizontal circle parallel to the ground at a constant speed. And so we're given radius of this circular path is 0.36 meters. And if the sun is traveling at 1.88 meters per second, what is the angle theta between the string and the vertical direction? Um, so velocity is equal to 0.88 meters per second. And so we're tasked with finding theta. Um, so this one is gonna use our mv squared over r. And then you're gonna split this into two components. You're gonna split it into an x and a y. Um, so let's start with this, right? So when we split it, we say this is tension y, and we say this is tension x. And so what this is going to allow us to do is it'll allow us to use our trig functions, and we say this now, tan theta is equal to opposite over adjacent. And now we have our opposite, which we're going to call Tx, and our adjacent Ty. So when we plug it in, we get this. And we can cancel our masses. And now we have tan theta is equal to v squared over rg, and theta is equal to tan inverse of 0.88 meters per second squared over times gravity, which is 9.81. Okay, and then, sorry, that's like really sloppy. Okay, and then from there you just solve, and that should give you the correct answer. Yep, and so this gives you theta is equal to 45 degrees. Okay. So that's 2. And then for 3, we're told a person who has weight W on Earth's surface travels to a remote planet. That new planet has a mass that is half of the Earth's mass and a radius that is twice the Earth's radius. What is the weight of the person close to the new planet's surface? Um, wait. Okay, so we know this. Um, and so we're told that the mass, so force of gravity is equal to weight, basically, right? Or we can say mass times gravity, which is equal to weight. So you know this is equal to mass times gravity, right? Um, and so if the new planet has mass that is half of the Earth's mass, then we know this, right? And if we say that the radius is twice the Earth's radius, we know this, 2r squared. And so from here, when we reduce everything, we say this over 2, right? Because we're going to take this 1/2 and we're going to move it to the denominator. And so we say 2, and then we're left with times 4r squared. Um, and so you can see here that the weight on this separate planet, on this different planet here, weight is going to be divided by 8 in the denominator, which leaves us with this, right? Because this is weight on the different planet. Weight on new planet. So this 8 in the bottom, it's reflected here. Don't make the mistake of like moving the 8 to this side and then ending up with 8. Know that like the math that was done here, right? These were the adjustments that were made to make this the weight on the new planet. And so it's divided by 8. Okay, so that's 3. Um, yeah, maybe to make this more clear, I should say like this is like weight new. So yeah. Okay, that's 3. Let's do 4 now. So the car drives around a curve in a frictionless banked road as depicted in the figure below, where the road makes an angle of 30 degrees. If the curve has a radius of 50 meters, then what is the fastest speed at which the car can drive? Okay, so the thing that's going to be keeping the car moving in a circle again is going to be our centripetal acceleration. So AC keeps car on the track. Okay, and then just looking at this, the only thing that's only force that we're given or that can act and supply the centripetal acceleration is gravity. And so gravity here, and um, that means when we take our formula, mv squared over r, we're going to be solving for the velocity. So just to check, yeah, so we're going to say that this is the normal force out, and this is theta, right, opposes, and v squared over r. So to solve for this velocity, we're gonna say tan theta is equal to, again, opposite over adjacent. So m v squared over r is mass times gravity. And the reason we have to do this is because in this formula right here, we need the mass, and we're not given the mass in the question. So we have to find a way to cancel the masses. Um, so here, cancel the masses. And so now we say this, tan 30 degrees is equal to v squared over rg. And so then we solve for velocity, and we say that should give us the answer, tan theta times 50 times 9.81 square root. Yeah, that's right. Um, so to be a little bit more clear, we can say tan 30 degrees times 50 meters times 9.81 meters per second squared. All of this near square root equals velocity. So that's 4. Okay, and then 5. We're given a satellite with mass 4.2 times 10 to the 5th kg in a circular orbit around the Earth. The mass of the Earth is 5.97 times 10 to the 24th kg. If the satellite has an orbital radius of 6.78 times 10 to the 6 meters, how long does it take for the satellite to complete one orbit? Um, so again, we can use this formula, I think. T equals 2 pi r 3 halves over square root GME. Either we'll use this formula, or we're gonna use this formula, right? Those are basically our two like possibilities. But just looking at this, because it's like a satellite orbiting the Earth, we're gonna pick this one. Um, and so plugging in everything, we can say, yeah, okay, that is right. Okay, so we say this, and our radius of 6.78, the 3 halves over square root G, and mass Earth. which is given 5.97. It's 10 to the 24th kg. Okay, and then when you solve, that should give you the correct answer. Yeah, so it gives us this. And that's approximately what we get here. That's a good question. I don't know why it gives the mass of the sunlight. It does make it confusing to have like both, right? Um, yeah. Just know like if you see time, like these are your two equations that you have for time, or period, I guess. This second one is gonna be used more for like pendulums and stuff. But this top one is gonna be used more for like satellites, planets, whatever. Um, so yeah, it's tricky when you see like this mass because then like when you look at this equation, you're like, why don't you use it? Um, but yeah. Okay, so that's 5 and 6. I think this is should be okay. This is pretty similar to the one we did earlier. So again, we drop the ball from rest at a height of 2 meters and it takes 1 second for it to fall, right? So again, like we did earlier, we're gonna start with this and hopefully plug it into this. Um, so let's cancel this. Let's say 2 meters is equal to 1/2 a 1 second quantity squared. So 2 times 2 gives us 4. So acceleration is equal to 4 meters per second squared. And this is our gravity. Um, and so we can plug this back into here, right? And so we get mass 1 times 4 meters per second squared is equal to g m1 m2 over r squared. We cancel these two, and now we're left with, um, let's go ahead, since we're solving for radius, let's go ahead and move the 4 meters per second squared to the other side and move radius to this side. So let's say this, r squared is equal to sorry, g m2 over 4 meters per second squared. Um, and we're told M2 is this right here, right? And so from here we can just solve and that should give us the right answer. Yeah, it gives us R is equal to 9.94 times 10 to the sixth, which we see here. And I probably should have said this earlier, but the G that we're using is this 6.626 times 10 to the negative 11th, and that's given in your formula sheet. It's this one. So I guess it's 6.67. So I guess I've been using, I remembered it wrong. Um, but yeah, it's this in the formula sheet. Um, so yeah. Do the planets make a lot more sense now, or like are there things that are still confusing about them? I know someone asked like earlier, or was saying that they were kind of confusing. But do they make more sense now, or is like something still confusing about them? Okay, good. Good. Okay. So I guess moving on, number seven. So we have this, we're told a 2 kg block slides down a 1.36-meter ramp with an unknown coefficient of friction, and the ramp makes an angle of 36.9 degrees with respect to the horizontal. If the block has a speed of 1 meter per second at the top of the ramp and a speed of 3 meters per second at the bottom, then what is the net work done on the block by external forces as it slides down? Um, oh, okay. So let's just start with the picture. And we have this 1.36-meter ramp. And we start with this block at the top. That's 2 kg. Okay. And this angle at the bottom of 36.9 degrees. Okay. And so we're told the block at the top has a speed velocity initial of 1 meters per second and speed velocity final of 3 meters per second at the bottom. So the net work done on the block by external forces. Um, so this again is going to make you think of work energy theorem. So work energy theorem. And so what work energy theorem again tells us is work is equal to the change in kinetic energy, or basically just like the change in energy at all, right? Or basically the change in energy. Um, so remember we set up with our energy questions, we set up this, the potential energy initial plus kinetic energy initial equals kinetic energy final plus potential energy final. And the difference between these two, the difference between initial and final total energies is going to give us this work here that we want. So let's start with our potential energy initial. Um, it's going to be mass times gravity times height, uh, plus, let's just write it out like this first, and our potential energy at the bottom is zero, right? Because it has no height. And so this is initial and final. And so we say 2 kg times 9.81 meters per second squared times our height of whatever this is, right? And so we're going to have to use our trig function to get that. So we'll say this sine 36.9 degrees times 1.36 meters is equal, and we have to do our kinetic energy too, right? So plus 1/2 mass of 2 kg, and our velocity initial is 1 meters per second squared. So we say this 1 meters per second quantity squared is equal to 1/2 velocity final squared. And that's going to be 3 meters per second quantity squared. So when we solve, we're left with, let's see what we have on each side. So we're told, or we're given this 17.02 joules on the left, and we get this on the right. We get 9 joules on this side. Um, and so between these two, our change in energy is 8 joules. Um, is 8 joules, and so we know now that it's this. Um, I'm actually not sure why it's positive. Um, I don't think I wrote that down either, why I said it's positive. Yeah, I guess if someone knows why it's positive, they can put it in the chat. Um, but yeah, I didn't even think to check why it would be positive before this. Um, so yeah, so that's 7. So number 8, let's see, this is similar to what we did on the 2024 exam. So normal force here, again, since our distance, we have, when we do work questions, we say this work equals force times distance, and this distance is parallel. And since we have no displacement parallel, our normal force is equal to 0. Okay, and for 9, the tension force, so this force provided here, what is the work done by that force? Again, since we only work in parallels, we don't have any vertical displacement. That means we have to work only in the x direction because we only have x displacement right here, right? So that means we have to adjust our tension force. And so we say cosine 30 degrees times our tension, which we're given is 300 newtons, so times 300 newtons times displacement parallel of 4.0 meters. And so then you just solve and you get that. It should be correct. Yeah, it gives you this. So that's 8 and 9. Okay. So moving on, number 10. So we're given two objects and one of mass 2 kg and one of mass 4 kg. They're dropped from a height of 40 meters. And then we're asked what is true about the two objects before hitting the ground. Um, so basically, they're asking to find like the relationship of the kinetic energy between the two. And so looking at our formula, we have this 1/2 mv squared equals kinetic energy. From here, we can see that kinetic energy is directly proportional to mass. And so since it's directly proportional, a 2 times increase between object 1 and object 2 is going to yield you this one. So have your object will have twice the kinetic energy. And that's because they're directly proportional as given by the formula. So yeah, that's pretty simple. Okay, so 11. Um, 11's a little bit more tricky. I guess we haven't done one like this yet. But we're given this height at 3r. Um, and we're told when the block passes through loop B, what is the normal force from the track acting on the block? Okay. And so logically thinking about this, as it passes through point B, our radius here is going to be actually 2R, right? And so thinking about like the energies that we start with at the beginning we have mgh and we have mgh here plus kinetic energy, right? But the difference between point A and point B is that at point A we have 3R, so mg3R, and at point B we have mg2R. Um, and so putting this into like an equation, we can see this. And when you move it to the other side, mgr is equal to the kinetic energy. Uh, and so this normal force here that's acting perpendicular is going to be supplying our centripetal acceleration. And as we noted earlier from other problems, the centripetal acceleration is related to the kinetic energy through velocity, right? So because AC is equal to V squared over R, we can connect it to our kinetic energy. Um, and so let's see, just to make sure. Yeah, so I said this when I solved it earlier. I said 1/2 v squared and 2gr square root is equal to velocity. Um, and so this velocity here is going to give us this over here. And so since the normal force is going to be making up or compensating for this extra centripetal acceleration, as we see, like uh this is like what we're aiming for, right? So from here we can say this um right? And so then when we plug it in, we have this. And okay. Um, so yeah, these I feel like are really, they're kind of just tricky to explain. Um, yeah, I wish I could like, I wish I could teach these a little bit better. Um, but this is like, at least from like a math standpoint, that's how you do them. Um, but in terms of explaining it, feel like these are kind of hard to explain. Um, but yeah, so that's 11. Um, we'll look at one more of these, um, just so that they make a little bit more sense. But yeah, I feel like these are probably like one of the harder questions on this exam. So, number 12, we're given this 3 kg block. It's on a horizontal surface at rest against a horizontal spring, and we're told this spring is K is equal to 2000 newtons per meter, and distance is equal to 0.20 meters. And if you remember our spring formulas, we have this and this, but I'm not actually sure. I'm not sure if these will actually come into play or not for this question. Um, so the spring is released and the block begins to slide across the surface with the coefficient of kinetic friction equal to 0.4. So how far does the block slide before coming to rest? Um, so basically we find the potential energy in this spring, and then that will allow us to solve for um, the work required for it to slide x distance, right? So this is our spring potential energy formula. And it's on your formula sheet as this U elastic is equal to 1/2 kx squared. So that's where it is there. Um, and so solving, we have U is equal to 1/2 2000 Newton meters times x squared, which is this 0.20 meters quantity squared. And so when we solve, we get 40 joules. And so from here, we'll use this to calculate distance. The other thing that's like interesting or like you could use is like this 40 joules is equal to 40 Newton meters, right? So like from here you can see your force times distance, right? You can see your work, right? Because force equals newtons and distance is meters. So that's like pretty interesting to see, right? Um, so from here we say 40 joules is equal to this force here, kinetic friction. So we're saying force of friction is equal to mu k times n, and mu k times mass times gravity, since n is equal to normal force, which is equal to mass times gravity. And so now we have this 0.4 times 3 kg times 9.81 meters per second squared. And then we solve and we say is equal to 11,772. This is in newtons. So we say 11.772 newtons times distance. And solving, we get distance is equal to 3.39 meters. So that's that one. Yeah. So there's not that many spring questions. But yeah, I guess just to be prepared, they're pretty similar to the energy questions. Like in terms of setup, instead of using like MGH, right? You're just using 1/2 kx squared, which is just for the spring. Um, so yeah, it's not any different than like what you've done. It's just dealing with springs instead. Um, so let's see 13. This is a power question. Um, so we know power is equal to work over time. But since we know work is equal to force times distance, we know then that power is equal to force times distance over time. And we know velocity is equal to distance over time, right? So we also know power is equal to force times velocity. Let's see if this is on the formula sheet. Yeah, it's right here. So power equals force times velocity. I'll say right here, power equals work over time. Um, So that's just this is just the derivation of like how they're related, right? So work over time and then work over time. Since work equals force times distance, we're going to say force times distance over time is equal to power. And since velocity is equal to distance over time, now we're left with power equals force times velocity. And so this question's kind of interesting because you look at it and you're like, okay, well, the velocity is obviously like this, right? 50 meters for over 30 seconds. So like just solving this is distance 50 meters over 30 seconds. Velocity is equal to 5 over 3 meters per second. Like that's pretty simple, right? But then like you ask yourself what the force is, and like that's a little bit more confusing, right? But what they're getting at with this question is that the force is actually due to gravitational acceleration. So when we solve for force, we're going to use 1300 kg times 9.81 meters per second squared. Um, and so putting these two, putting like the force and the velocity together and multiplying them, that should give us our correct answer. Um, so, and that gives this 21,255, and power is measured in watts. And so written in scientific notation, it is this. So yeah. Um, yeah. Okay, so 14. I think the impulse question is here. Yeah, the impulse is 16. So we'll cover that too. Um, so number 14 first before we get to the impulse question. Um, we're given the mother penguin and it slides down an icy hill with height 5.1 meters. Scoops up her baby at the bottom of the hill. If the mother has a mass of 20 kg and the baby has a mass of 5 kg, what is the speed of the two of them after their collision? So this one's like a really simple momentum and energy question again. So momentum and energy. So at the top, the energy that the mother penguin will have obviously is mgh, right? So we know this times 5.1 meters. And so when you solve it, it says 1,000 joules. So that means at the bottom, the penguin will be going at 1,000 joules, um, because this is going to be converted to kinetic energy, right? So here at this point, potential energy, but right before it hits this penguin, we have kinetic energy. So we can solve for velocity. So we want to solve for velocity here, which will allow us to do momentum and collision, right? So we have 1/2 mv squared, and this is 0.5 times 20 kg times velocity squared. This is unknown, right? But this is all equal to 1,000 joules. And so velocity squared is equal to this turns out to be 10, right? So this is 100, and so velocity is equal to 10 meters per second. And so Now we have our simple momentum, and so now we say momentum initial is equal to momentum final. The small penguin is at rest, so that means we just have 20 kg times 10 meters per second plus 0 is equal to momentum final. And so momentum final is going to involve this 20 plus 5 kg, right? Because they collide and the speed of the two of them after their collision, they stick together, assuming this, well, she scoops her up, right? So they stick together. So 20 plus 5, so we have 25 kg. And we're trying to find this velocity final is the thing we're solving for, right? So then we solve and we say this is 200 kg meters per second over 25 kg, and that gives us our velocity final. Velocity final is equal to 8 meters per second, which is our answer right here. So, all right. So again, 15. Like I said, like these bullet questions are pretty common, pretty popular. This one just combines like energy and momentum together. So how much higher is it? This is going to be our energy portion, right? So this is energy and momentum. Okay, so we have m is equal to 0.040 kg for this initial bullet right here, and velocity is equal to 200 meters per second. And this second block is 1.96 kg. So obviously, after they collide and stick together, this whole system is going to be 2 kg, right? The question is like how much higher is it when it's freely hanging? And so to calculate this, we're going to find the kinetic energy of the system at the bottom and what it converts to as potential energy at the top of this swing. Um, so to solve for the kinetic energy, we have to use momentum. So we say 200 0.040 kg plus this 0 from here, and this is 2 kg velocity, unknown. And so now when we solve for this, we're given 8 kg meters per second over 2 kg is equal to velocity final. And so then we cancel and get this 4 meters per second equals velocity final of this 2 kg system, right? Okay. So from there, we can solve for kinetic energy, and we say 1/2 mv squared and 1/2 2 kg velocity final squared. This 4, so we say 4 meters per second squared. And from here, there's the kg, 2 kg and the 1/2 are going to cancel. So we're left with 4 joules. So now plugging this in to our potential energy, we know kinetic energy is equal to like this potential energy at the top. So we say this 4 joules is equal to mass times gravity times height. So 4 joules, said earlier, mass is 2 kg times 9.81 meters per second squared times height. And solving for height, that gives us our answer. 4 divided by 2 divided by 9. Oh, it looks like I did something wrong. Let's see. Mm, oh, this is wrong. I didn't square this right here. Right. So this actually should be, yeah, it should be 16 joules. Yeah, nice catch. So that leaves us here with 16 joules, 16 joules. So we have 8 divided by 9.81, right? And so that gives us our answer. Sweet. Yeah, it's not bad. All right, and 16 is the impulse question. Um, so impulse on your formula sheet is given as J, and it's just change in momentum. And the little arrow on the top is just telling you that they're vectors. So you have to include direction when dealing with impulse. And so on your formula sheet, it's this right here, this formula. Um, but it turns out it's not as difficult or as hard as it looks. So since impulse is change in momentum, our momentum initial is, let's see, the ball is 0.50 kg, and it's traveling to the right at a speed of 30 meters per second, and then it's traveling to the left at 20 meters per second. And so we're asked to calculate the impulse. So let's just set, since it's already set, this is positive and this is negative, right? Our momentum initial is equal to 30 meters per second times 0.50 kg. And that leaves us with 15, right? Kg meters per second. And then on the flip side, this negative 20 momentum final is equal to negative 20 meters per second times 0.50 kg. And we're left with negative 10 kg meters per second. And so um, when we set up our delta P, we're given this. So delta P is equal to momentum final minus momentum initial, right? And so when we plug this in, we get momentum final, negative 10 kg meters per second, minus positive 15 kg meters per second. So 15 kg meters per second. And that leaves you with negative 25 kg meters per second. And again, like I said, since we have these arrows here, it tells us that they're vectors. So we have negative, negative here. They're moving towards the left. So that's why when we select it, we get 25 kg meters per second to the left. So yeah, okay. Anything about the impulse question? I know this one is new, or we haven't covered it yet. So yeah, and the power to anything over those two. Okay, I guess not. Okay, so yeah, 17. We actually moved through a lot faster than I thought. I only prepped 2 exams because I was like, each exam's gonna take like 2 hours, and then like the 2024 was half, so it's like 3 hours. Um, But yeah, I did not expect to be done this fast. Um, so 17 is on an icy road. A truck with a mass of 2,400 kg is traveling due east at a speed of 20 meters per second when it collides with the car with a mass of 1,600 kg. So this car is 1,600 kg and this truck is 2,400 kg. Um, the wreck of the two cars travels in direction 45 degrees north of east. What was the speed of the car just before the collision? So again, like we said, or like we set up earlier, we had our triangle, right? And since we know this angle exactly, right, this 45 degrees, we can actually use our trig functions to solve for this one. So this is like the truck momentum, and this is the car, right? So just working with these two, we can use tan theta is equal to opposite over adjacent. So tan theta, 45 degrees, is equal to our opposite, which is the car, right? Car momentum over truck momentum at the bottom. So we have truck P, right? And so solving for this, we can say 1,600 kg times our velocity unknown over this truck, 2,400 kg times 20 meters per second. And so when we solve, that should give us our answer, right? So tan 45 is 1, and then when we move this to the other side, you get 48,000 kg meters per second is equal to 1,600 kg times velocity. And so that leaves us with 30.0. So that's 17. So the same as like what we did on the 2024 exam. Um, but here for this one, we weren't given the angle. We were just told to calculate this velocity final. Um, but it's basically the same question, right? It's just you're given this same setup and everything. So okay, that's 17. All right, 18. We have two blocks with masses 2 kg and 4 kg held at rest on a horizontal frictionless surface with a compressed spring between them. Again, the spring holds 24 joules of elastic potential energy. The two blocks are released from rest and move off in opposite directions. And we're asked to find the final speed of the 4 kg block after leaving the spring. Okay. Um, this one again is going to be momentum and energy. Momentum and energy. So we're told this 24 joules. We know at the end that the momentum of the two blocks is going to be 0, right? Because momentum here is 0. So momentum here must also equal 0. And also that the kinetic energy here on this side is equal to 24 joules. Okay, so let's see. Let's set up like our positive and our negative. So let me just check and make sure I'm gonna do this one right. Um, yeah, okay. This one's a little bit harder. Um, so we're told 24 joules, and so since we have this kinetic energy on this side, we're gonna say this 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And let's call this let's call this m1. Let's call this other block m2. Okay, and so the key here is to use the momentum to help you eliminate or help you substitute one of the variables. So we know that momentum initial is equal to momentum final, right? Which means that m1 v1 plus m2 v2 is equal to 0. Let's swap these to be like a little bit more clear, right? Okay. And so that's from this 0 here, right? So momentum before is 0, momentum after must also equal 0, right? And they move in opposite directions, so we have this negative and we have this positive here, right? So we have, if we move this to the other side, we can say this m2 v2, and we can then say this, right? And so when we substitute this in, we'll just plug it right into here, and that will allow us to solve for velocity 2, right? Because we got rid of velocity 1. And since we're solving for velocity 2, this block over here, that's all we need. So let's put this over here. So now we say this, and we're going to plug this in, right? And since we're squaring the velocity, we can just drop the sign, right? And so, okay, and then we can simplify and we say this. Let's check that I'm doing that right. Um, oh, I actually simplified it. That's actually an easier way. Um, so what I said or what I took was since 4 kg is double this 2 kg, we can actually take this from this side and we can say since M2 is 2 M1, we can say then we can then say just this, right? 2 V2. And so that allows us for like a cleaner switch over here rather than all of this is kind of messy. So 2v2 squared, leaving us with 4v2 squared. And then from here, you can just solve 2 and say, again, you can do the same thing with like this M1 and this M2, but it's not that necessary. You can just say 1/2 times 2 kg times 4 squared plus 1/2 times 4 kg v2 squared. And now we're left with this. This is okay. And then we can just add these together and we're left with this 6 kg V2 squared, 24 joules. And 24 divided by 6, obviously, is 4. And so then when you solve V2 is equal to 2. And that's our answer. Yeah, that was harder than I thought. Um, yeah, maybe there's like a faster way to do it, but this seems to be like the most effective way, so yeah. Okay. All right, so 19, we're given a projectile with mass 3 kg and a speed 8 meters per second fired at a block with mass 5 kg next to an uncompressed spring with a force constant of 500 newtons per meter. The projectile sticks to the block, causing it to slide into the spring. What is the maximum distance by which the block will compress the spring? Um, so this one, again, we'll use our spring equations, which is this kx squared. Um, and basically the idea is that your energy here is going to be converted. So energy from ball converted to elastic potential energy. Okay. Um, and so when we do this, we'll first use the momentum here, like between these two. We'll calculate momentum. We'll convert what we get here from momentum into energy. And from there, we'll solve this elastic potential energy. Um, so it looks like actually, yeah, okay. So we're given this 8 meters per second times 3 kg. And this 5 kg, they're going to stick this 5 kgs at 0, right? But they'll stick together for a total of 8 kg times velocity final. Okay, and so just looking at this, we know this 24 kg meters per second is equal to 8 kg velocity final. Velocity final is equal to 3 meters per second. And since they're stuck together, um, we can use 8 kg as the total when we plug it into our kinetic energy equation, right? And so this gives us 4936 joules, right? 36 joules. And so that's our elastic potential energy, right? But then we plug this into this equation over here. And so now we have 36 joules is equal to 1/2 kx squared. And so when we multiply, we get 72 joules is equal to kx squared. Um, and then 72 divided by 500. So K is equal to 500 newtons meter, right? And that's provided here. And so then when you take the square root, so let me just write this out, over 500 newtons per meter is equal to x squared. And so x, when you solve for it, is equal to 0.379 meters, which we know then is 38 centimeters, giving us this answer right here. So yeah. Okay, so 20, we're told a small car collides head-on with the large truck. Which of the following statements is correct about their collision, considering the system to be the car and the truck? Um, so this is like the same thing as like what we have here, right? So based on like the way we solve these, we know for sure um momentum is conserved, right? Um, so that means we can lose C and D. So between A and B, again, like I said in recitation the other day, kinetic energy is not always conserved because some of it is going to be lost to sound, heat, light, whatever, right? So that's why A is wrong, leaving us with B as the correct answer. So, yeah. Um, that's all I prepped for today. That was like we got through that way faster than I thought. Um, but yeah, it seemed like everybody made it already, and like there's nobody that's coming from like 8 to 9. Um, but yeah, I guess we can be done here. I'll stick around for like questions. If you guys could you give a rundown? Yeah. Um, I think the only one that you need to know for exam one or know when to use is this delta X one. Wherever it went. I don't know where it went. Oh, it's right here. Um, and this one is just because it gives you this acceleration. Um, I'm pretty sure this is the only one they'll ask you to use again. Yeah, I used some of the ones for calculating the power, right? I used distance over time here, right, for calculating power. But that's not necessary unless you want to derive it because it's given right here, right? But yeah, you'll need to know friction, right? Um, this spring equation, like I haven't seen it used anywhere. Um, so probably like it's probably not that useful. But do you know your friction? Do you know this one for the like specific question with like the weird gravity? Um, but I don't think other than that you'll need much other ones. So are you asking which one again? Like which equation? You know this one, right? How will we know if we need static or kinetic friction? Um, Static friction is just if the object's moving, and kinetic friction is just if the object's moving. But like, yeah, I mean, I guess just know like if it's kinetic, I guess we can say this, right? And not moving, right? But when you apply them, they're basically the same thing, right? The formula is not any different. This is just saying like this inequality here is saying like if your mu static, if this is greater, it exceeds this static friction, um, then it's going to be converted to kinetic friction. That's all it's saying. Um, but just know, like when you apply them, they're basically the same thing. So yeah. Yeah, sorry we're ending like kind of I guess we're ending a whole hour early. I just didn't think that we'd make it through that fast. So can you go back to 20 from the other exam? Yeah. This one? Yeah. All right. I will keep you in my prayers. Does everything like make a little bit more sense now? Was this helpful for you guys? Okay, good, good. Okay, that's actually good to hear. Yeah. Okay. Yeah, it's been recording, so I'll send it. Okay. Anything else? Sorry about this que these loop questions. Like I honestly don't really understand how to explain them. Um they're just kind of tricky. But look at them, I guess look at it over again. I think there's one on 2022 that you can look at also. Just put it into chat, like it'll help you solve it. So, okay. Well, anything else? If not, I guess we can just end the meeting already then. Um, all right. Well, good night, y'all. Okay, good luck. Y'all are gonna do great. So, yeah, of course. All right. I'll see you guys. Let's see, how do I even end this?